Question number 12, which says that a quantity of electricity liberates 3.6 grams of silver from its salt. What mass of aluminium will be liberated from its salt by the same quantity of electricity? A 2.7 grams, B 1.2 grams, C 0.9 grams, D 0.3 grams. Alright, in order to solve this question, let's simply grab our pen and calculator. So we start first by extracting our parameters. We have that a quantity of electricity liberates 3.6 grams of silver. So we'll start with mass of silver liberated. Mass of silver liberated is 3.6 grams. Okay. What mass of aluminium will be liberated from a salt by the same quantity of electricity? Okay, we don't know the quantity of electricity. All right. There's a formula for quantity of electricity. Q is equal to IT. But then where our I is the current in amperes and our T is the time in seconds. But the problem we have here now is that this question is not giving us the current that was used and the time taken. So we cannot really calculate our quantity of electricity from this. Okay. But the idea we will use here is that they say what mass of aluminium will be liberated from a salt by the same quantity of electricity. So we have that this quantity of electricity that we don't know liberates 3.6 grams of aluminium. Sorry, liberate 3.6 grams of silver. Okay. So in solving these questions, first thing first, we know that silver is a positive ion, and what really happens during electrolysis is that the positive ion will migrate to the negative electrode, which is the cathode. All right. So, and what will happen there is that the positive ion will take up electron. All right. It will gain electron. So, what really happens when there's a gain in electron is what we call reduction. So, reduction always happens at the cathode, while oxidation happens at the anode. At the anode, there will be a loss of electrons. So that is oxidation, because oxidation is concerned with loss of electron, while reduction is concerned with gain of electron. So at the cathode, there is what? There is reduction, right? Which is accompanied by a gain of electron. While at the anode, there is what? There is oxidation, which is accompanied by a loss of electron. But we are only concerned with what? With the metal now, which is what this the positive ion, silver, of course. So it will migrate to the cathode. So what we expect is that what there's going to be a gain of electron. So this is what happens. Our silver ion migrating to the cathode now will have to take up an electron to be reduced. The number of electrons it's taking is equal to the charge it has, so that it will now be reduced to its normal. So at this point now we say that silver has been discharged. All right. Now the number of electron it gains equals what we call a Faraday. All right, Faraday. So the number of electron it gains equals the Faraday. So what we'll do now is that every 1 Faraday is equal to 96,500 coulombs. And the Faraday is responsible for discharging the original mass of the substance. So here now that we have silver discharge here, we have only 1 Faraday responsible. So if we have other atoms, we might have 2 Faradays responsible, 3 Faradays, or 1 million Faradays, depending. Okay. All right. So here now we have only 1 Faraday. So this is what we'll do. We will kind of equate it mathematically. All right. So we say that here now we only have 1 Faraday. So 1 Faraday, all right, liberates what? 1 Faraday liberates our silver, and the original mass of silver is taken from what? Its mass number. So the mass number of silver is 108 grams per mole. All right. So we say that 1 Faraday liberates, I like to equate it mathematically. Okay. Liberates 108 grams of silver, or discharged 108 grams of silver. This is the original mass of silver, right? So now we have a particular mass of silver that was also discharged. This was the mass of silver liberated. All right, this one here now is the original mass, so 1 Faraday is responsible for that. But this silver, that the grams of silver that was liberated, now we don't know the quantity of electricity that is responsible for the discharge of it. Okay, we know that Faraday is always responsible for discharging the original mass of substances, and the original mass of any element is the mass number. Okay, so this mass of silver that was liberated, now we don't know what quantity of electricity is responsible for it. So since we don't know, we have to put our Q here, but we know that it liberates 3.6 grams. Okay, don't forget that 1 Faraday is equal to 96,500 coulombs. Okay, so we can just change this our 1 Faraday to 96,500 coulombs. Okay, so now what I love to do is to think of it like there's a division line here and there's a division line here, and I cross multiply. So if we cross multiply now, we're going to have what? We're going to have Q times 108 equal to 96,500 coulombs multiplied by 3.6. So we'll divide both sides by what? 108. I'm trying to do it in the best way that you can understand it. Okay, so 108 will cancel out. The quantity will now be equal to 96,500 times 3.6 all over 108. So 96,500 times 3.6 will punch our calculator. Alright, so we'll have our 96,500 times 3.6. We'll have 347,400. So 347,400 divided by 108. So we divide by 108. Okay, divide by 108, and then we'll have our quantity to be 3216.6, approximately 3217 coulombs. So this is the quantity of electricity that liberated 3.6 grams of silver. All right, so but then they are asking us that if this quantity of electricity liberates 3.6 grams of silver, what mass of aluminum will be liberated from its salt by the same quantity of electricity? So from the information that was given to us in the question, we understand that this same quantity of electricity is responsible for liberating a particular mass of aluminum, right? But we don't know that mass, and we are asked to find it. So, but we know that this same quantity of electricity that liberated 3.6 grams of silver also liberated a particular mass of aluminum. All right, so the next thing we're going to do is to find the number of Faradays that liberated the original mass of aluminum. Don't forget the number of Faraday that liberated the original mass of aluminum. Okay, so how will we find that? We know that aluminum ion, right, will migrate to the cathode. Aluminum ion will migrate to the cathode, and then it will take up electron so that it will be reduced. Okay, so it will take up electron, and I told you that the number of electron it will take is equal to the number of charge it carries. So since it carries 3 charges now, that will be what? That will be 3 electron to give us our aluminum. All right, so it means that 3 Faradays was responsible for liberating the original mass of aluminum, and 3 Faraday is equal to what? 3 times 96,500 coulombs. Don't forget that a single Faraday is 96,500 coulombs. Okay, so now that we understand that, we will now say that our 3 times 96,500 coulombs, which is the number of Faradays that is required, liberated the original mass of aluminum, and the original mass of aluminum is 27. Okay, so we are told that the quantity of electricity that liberated 3.6 grams of silver was also responsible for liberating a particular mass of silver that we don't know. Okay, so and that quantity of electricity is 3,217 coulombs. So we'll have it here, 3,217 coulombs. It was responsible for liberating a particular mass of aluminium, but we don't know that mass, so we'll just put M, right? Then, like I've told you before, imagine a division line here, so you just cross multiply. You have M times 3 times 96,500 coulombs equals to 3,217 times 27 all over 3 times. So at this point now, we divide both sides by 3 times 96,500 so that we'll have our M alone. This is just mathematics. 3 times 96,500. Oh my bad, you're not seeing it. Okay, so this is what we're doing. Okay, at this point, we'll 3 times 96,500 strike out here. Then we'll have our M to be equal to. So we grab our calculator and calculate. Permit me to do the calculation outside the background. So we'll have 3,217 times 27 to give us 86,859 all over. Then let's do our 3 times 96,500. 6,500. We'll have 289,500. So let's divide 859. 6,859 divided by 289,500, and then we'll have our answer to be 0.3 grams. So this is the mass of aluminium that was deposited when the same quantity of electricity, 3.6 grams of silver, was used to liberate the mass of aluminium.